Watch a child athlete burst off the line, and you are seeing a body in a unique, rapid state of flux. This biological engine operates under specific rules. The narration and analysis within this video have been prepared by Dr. George Panayiotou. For decades, coaches mistakenly treated children as smaller versions of adults. This approach ignores the reality that a young body is evolving physically and chemically at a rate that adult models cannot predict. Realizing a young athlete's lifelong potential requires a different approach. We have to follow a 7-step pediatric blueprint that respects their unique biological machinery, moving from microscopic cells to macro-level health. This blueprint separates physical progression into a triad. Growth is the change in size. Development is the shifting of specialized functions. And maturation is the progress toward a fully functional adult state. Chronological age is an unreliable metric for sports because biological maturity can vary by up to 5 years among peers. This X-ray of an 8-year-old girl's hand is the standard tool for measuring true skeletal age. Specialists track the proliferation of cartilage and its subsequent ossification into bone. The amount of cartilage remaining reveals the child's actual progress toward a mature skeletal state. The critical milestone here is peak height velocity. This tracking metric identifies the maximum rate of growth occurring before puberty, signaling a window where the skeleton is particularly sensitive to physical load. A child's smaller heart results in lower stroke volume, requiring higher heart rates to move blood to working muscles. Metabolically, children are non-specialists. Their limited glycolytic capacity makes short-burst anaerobic work difficult, but high levels of oxidative enzymes allow them to burn fat for fuel much more efficiently than adults. Cooling is another distinct disadvantage. Because children have a larger surface area to mass ratio and fewer active sweat glands, they absorb environmental heat faster and dissipate it through evaporation more slowly than adults. Because a child's cardiovascular and metabolic systems operate under these different biological constraints, applying adult training intensities to their machinery is physically reckless. To apply this safely, we must evaluate motor skills and aerobic capacity. These boys are the same age, yet their varying sizes indicate vastly different levels of physical readiness for high-intensity training. Properly supervised resistance training yields significant gains. However, a child must demonstrate absolute movement competency and technical mastery before any external weights are introduced to their program. During growth spurts, coaches must track subjective fatigue to prevent overtraining. We use specialized tools like the Omni or CERT scales, which allow youth to accurately report their level of perceived exertion. These assessments build the process framework, incorporating progression and regularity. This model converts the chaotic variables of youth growth into a predictable, measurable blueprint for development. To protect developing joints and match their limited glycolytic capacity, the program uses 1 to 3 sets of high repetitions. This volume builds muscular endurance, while loads only increase by 5 to 10%. Rigorous assessment and the process model ensure that physical training works with the child's biology, turning the rapid changes of youth into safe athletic gains. The psychosocial environment is just as critical. While early stressful specialization leads to high burnout, diverse athletic exposure and autonomous free play foster the cognitive resilience needed for long-term sports participation. Intrinsic motivation and fun are biological necessities for growth. Without them, even the most scientifically perfect physical program fails to keep an athlete engaged long enough to adapt. For children lacking initial sport-specific skills, supervised resistance training serves as a gateway. It provides a controlled environment to build foundational strength and the confidence required for more complex sports. Prioritizing psychosocial well-being ensures that a child remains in the sport long enough to realize the physical benefits of their training. Adolescence provides a brief window of opportunity where the body is uniquely primed to build physiological reserves that will last into adulthood. Lifting weights during this specific window increases bone mineral density, building a skeletal structure that resists degradation through later life. Proper biomechanical training during this phase also fixes neuromuscular deficits. This reduces the risk of severe ACL and overuse injuries, providing a structural foundation for long-term health. The impact of this blueprint extends to the brain. We see a direct link between consistent physical activity and the development of superior academic focus. Neurological adaptations from this activity include enhanced executive functions, superior working memory, and significantly greater cognitive flexibility during critical tasks. Respecting the unique physiology of children builds effective athletes. These early adaptations also provide the biological framework for resilient, sharp-minded, and healthy adults. This scientific material and analysis was prepared by Dr. George Panayiotou.